Hello everybody. Thank you for taking some time to attend this tutorial for focus stacking for optical microscopy. So I'm going to start off here by showing you a video of crystallization. This is by National Geographic. So these are different metals that are crystallizing in solution that you can see here. You can notice the little crystal structures all around here, and these are for all kinds of different metals. And something that you can notice is that certain parts of these crystals are focused and detailed, but you can also see that other parts, maybe farther away or a little bit closer to the camera, are a little bit blurry. And this is a result of having a different focal length for different parts of the image. So for any given camera, you can only focus on kind of one distance away from whatever you're recording. And this phenomena is for all kinds of cameras, normal picture ones like you'd handle yourself, but also with microscope images as well. So wouldn't it be handy if we could somehow construct an image that is focused for all distances away from a sample? And that's what we're going to be trying to tackle today in this tutorial. So let me stop the video here. To illustrate, I have an image or images of a fly here. The one on the left is focused on the fly's head, and the one in the middle is focused on the fly's rear. And what we'd like to do is have a computer say, okay, well, this is the part of the image on the left that's in focus, and here's the image on the right that's in focus. Let me just take those two specific segments, and let me combine them together to form one complete and in-focused image. And we are going to be doing this with bismuth samples. Bismuth is an element, and it kind of sits close to lead on the periodic table. It's very, very heavy. And bismuth exhibits this kind of hoppered crystal structure. And this is this kind of stair-step or staggered way that the bismuth crystal solidifies. So when it's liquid, a small nucleus of solid will form. And as that nucleus begins to grow and solidify, the edges of that crystal preferentially grow. So what you get is this kind of stair-step pattern. The data that we'll be using, that we recorded at McMaster, is of a bismuth sample. And this video, we're actually tuning the focal length of the microscope on different portions of the sample. So starting out, we're here at the back, and gradually we go to the front to focus on the top of the crystal closer to the camera. So here we have two images that we've extracted from that video, and you can see what portions of the image are in focus and not in focus. And we'll be using a total of 4 of these images at different focal points to make our combined image. Now the question is, how do we describe an image to a computer? How does a computer interpret it? And here is a picture on the left-hand side of Abraham Lincoln. That's very, very pixelated. This is what we see, and this is what the display of our computers show us. But on the right-hand side, you can actually see what the computer is interpreting, or what the computer is actually storing as the image. It's just an array or a matrix of different data values that range from 0 to 255. And this 0 to 255 comes from computer's native language being in bits, zeros and ones. So this image, for example, is an 8-bit image, where 2 to the 8 gives you 256 different values, which goes from 0 to 255 for a total of 256 numbers. And we can see from this middle image here, where both interpretations are superimposed, that Abraham's beard is very dark, so the values are low, and the intensity of the pixel is low. While on his skin, it's brighter and closer to the maximum value of 255, ranging from about 240 right in the middle of his forehead. So computers interpret images as kind of collections of numbers, but how can we describe sharpness and blurriness, or in-focused and out-of-focused images? So here I have 2 images of bismuth crystals that are grayscale, or just black and white. And the image on the left is clearly in-focused and nice and sharp and detailed, while the image on the right is not so much. And if we zoom in to, say, this portion in the top middle of each of the images, we can see a little bit more closely about what the differences in the images are. So the focused image on the right, you can notice, say, this kind of edge region here, where it goes from dark to light. Within the dark region, the values stay relatively similar, especially in this point here. They're all the same value of dark, more or less. But once you hit this transition region, you see that there's a sharp change in dark to light. And you can almost count the distance, or the rate at which the pixel values change. And if you look on the more blurry image to the side here in the same region, you can see that this transition, or edge, is much more gradual in terms of going from dark values to light values. So we can use this concept of changing values between pixels to kind of represent what it means to be sharp and blurry. And if I show you this example here, where on the very left-hand side we have a dark pixel and a light pixel, we can see that this transition, or slope, is very large versus something a little bit more gradual with the gradient here going from dark to light. The slope is not as steep. So we can characterize sharpness and blurriness by the size of the slope, or the size of the difference between pixels. So we can actually kind of create a sharpness map if you want. And here I have the example of an apartment building on the left-hand side. And here we just take the difference between every adjacent pixel in the x direction and in the y direction. And you can see the sky is very uniform. And in the derivative, or the difference of the pixels for each image, it's pretty much black. It doesn't change at all. But when you actually go to the edges and the detail of the building, you can notice that those are the most salient, or most present parts of the image derivatives. So the outline of what we're doing is going to be like this. We have 4 different images of a bismuth crystal. We're going to load them in to Python. And then we're going to take the derivative, or the difference between each pixel of all 4 images. And then we're going to select the highest values of those image derivatives among the 4 different images, and select which ones are the highest, and take those highest pixels and construct our fully in-focused image. So to get started, I'm going to ask you to first download some files that we've created here, as well as the data set that we're going to use. So let me stop sharing my screen, and I will bring up Google here. And what I will do is type in the link that we're going to use. Okay, so type in the following link above. We'll have it attached in the video description for you to be able to copy and paste as well. So just type it in here and press enter. And you should be taken to a Google Drive folder. This contains all 4 of our images or data set, as well as the tutorial notebook that you'll be coding in, and the master notebook, which has all of the completed code if you want to review it at any point. So go on ahead and just press this little down arrow here, and you can press download, and that will download everything within this folder. And once that's completed, you can go on ahead and click the notification, and it should start downloading directly onto your local computer. And then what you want to do is extract this folder. So wherever you stored it, you're just going to want to extract all. So with that all ready to go, next you're going to want to go to Google Collab. And you can go ahead and make a new link here. And when you get to Google Collab, you may have to sign in to your Google account, but eventually you should be greeted with this window here. You're going to want to go to the right-hand side and select Upload, and then choose File, and then go to wherever your extracted zip file or your extracted folder is, and then select Tutorial Notebook. And if everything goes well, you should be greeted with some code here. And this is just some background code that we've made to make the tutorial progress along a little bit more smoothly, with things like loading the image and constructing the final in-focused image, just to make things go along a little bit faster. Okay, so the next step is to actually load the images that we'll be using into the Google Colab environment. And to do that, you're going to press this little window tab on the left, and then you're going to go to this little up arrow with the file, Upload to Session Storage, and click that. And in your unzipped data folder, just select all 4 images here. And then press OK if you get any notification. And you should see on the left-hand side some loading icons. Okay, so you should have all 4 of your images open and ready to go. And if you'd like, you can click on the images and expand them here to see as you wish. So the first thing that we're going to do to program is just load in our images as these data matrices or data arrays. So you can go down to the bottom below this cell here, and to show these images that we've loaded in, we can type the following code. Image underscore gray, comma, image underscore color equals load underscore image, quotation marks, and we're just going to select the name of Bismuth 0 here. So bi underscore 0 dot png. And now to run this code, the first thing that you're going to want to do is go up here to runtime and then just run all. This is just going to run the above code and the current cell here. And to actually show the image, what we can do is press Shift Enter, and that will run the cell above and create a new cell below. And we can type in show underscore images, brackets, and then we're just going to do a square bracket, and then just type in image gray, comma, image color as before. Image gray, comma, image, image color. And then you can press Shift Enter, or if you'd like, you can just press the run cell here. And what you'll get is the grayscale, or just black and white bismuth image, as well as the colored bismuth image here. And if you're curious to see what this image means to Python, you can go ahead and scroll down here, and you can make a new code cell. And we can just type in image underscore gray, and then just press Enter to see what Python is storing this image as. In this case, this is the gray image. And we can see that it's an array, or kind of just a matrix, with the different pixel intensities that range from 0 to 255. And the data type is an unsigned integer, 8, meaning unsigned as in it's only ever positive. An integer meaning 0, 1, 2, 3. And 8 meaning there are 2 to the 8 different discrete values that these intensities can be. That is 0 to 255. Okay, so now what we're going to do is actually calculate the derivative, or the gradient of an image, to actually select which parts of the image are in focus. So to do that, we're going to do another code cell here. We're going to define a function. And to do that in Python, you start with def space. We're going to call our function gradient. Then we put in close parentheses and a colon. And for us, a function is just something that allows us to reuse our code within the function, so we don't have to keep calling the same things over and over again. Okay, so then when you're here, you can just press Enter, and Python will detect that you've written a function and kind of create a little tab for you at the bottom. This is a part of the syntax with a function, so you can't just start writing your function like this. You have to have that little indentation there to work with. Okay, so we're going to take the gradient of an image, or we're going to take the difference between every adjacent pixel. And you can imagine we can do it in the horizontal direction with pixels to the right taking the difference, or we can do it in the vertical direction and take the difference of the pixel values going down the image. So we're going to start with taking the x gradient, and we're going to actually create a variable and call it xgrad. And the way that we calculate it is going to be using something called np.diff. And what is np.diff? Well, np is a short form for numpy, and this is just a collection of code that other people have written that you can easily access and use yourself. So within numpy, we're going to call this thing called diff, which will allow us to take the difference between the pixel values in this array. And what we're going to do is going to say, okay, well, what do you want to take the difference of? We want it to be an image. But you'll notice that we get some squiggly lines here where image is not defined. And when we write a function, we have to specify what we're providing the function with. So right now, gradient doesn't really take in anything, but we know we want to give it an image. So what we're going to do is just type in image right there. So we notice how the squiggly lines have gone, and now we can continue on with our gradient function here. So we're taking the difference along the horizontal array. So for instance, taking 65 minus 79. So we're going to have to tell the numpy.diff that we're going in the horizontal. And to do that, we say axis equals 1. And we're going to have to do one last thing here that may seem a little bit strange, but we're going to have to type in append equals 0. And the reason we're adding this line at the bottom is because when you're taking the difference between two numbers, say 65 and 79, you only get one number back. So if we take the difference between 65 and 79 and 63 and 65, and we do it all along the horizontal, we'll get a matrix or an array that's the same size as our original image, just minus 1. And for convenience, we just want the images to be of the same size. So we're going to append a 0 at the end of this image gradient, just so that the image size that we have is the same for all of our matrices and all of our arrays. Okay, so we can take the difference along the x-axis and append just a value at the end to make things consistent. But we know that our original image is a uint8, or a unsigned 8-bit integer array. And that unsigned is important, meaning that you can't have negative values. But right now, if we were just to use this line of code for our gradient function, we would get negative values because, for instance, 65 minus 79 would be a negative. So again, to make our images consistent in the same data type, what we're going to do is we're going to say, just take the absolute value of this image gradient. We do that by calling numpy.abs all around our numpy.diff. And this is our completed x gradient. Okay, so next, while we're here, you can go ahead and copy that entire line and press enter at the end of the line of code. And you can just go ahead and paste the same line again because the y gradient is very, very similar. We're going to change our variable to ygrad, and the only difference here is that the axis is now 0. And this specifies to the diff function that we want you to take the difference going down. For example, 68 minus 79. Okay, so that's awesome. However, right now we're actually working with two different derivatives or gradients. And wouldn't it be convenient if we could somehow combine the two? So we're not just looking at the gradient in the x or just in the gradient the y. And one way that we can do that is kind of take the hypotenuse of both of these gradients. And that may sound a little counterintuitive, but you can imagine that you have, for example, the x grad, differences all going along in the horizontal. And these differences are kind of analogous to the slope, but even more so a vector. So for large differences, the vector would be longer, and for small differences, the vector would be shorter. And we can combine two vectors and find their magnitude by using the Pythagorean theorem. And that's what we're going to do here. So we're going to define something called mag for magnitude. And then we're going to do np.hypot for hypotenuse. And our two variables are going to be the x grad and the y grad. And so for each pixel in our image gradients, it's going to calculate the square root of the x value squared plus the y value squared. And this combines both of our gradients into a single gradient that we can use. Then two other additional steps to make sure that these data values range from 0 to 255 is that first we're going to normalize this magnitude by the maximum value in the array. So that means making this magnitude range from 0 and 1. Then we're going to multiply this magnitude by 255 to make it go from 0 to 255 now. So we have our completed function for defining the gradient. And now when our function has completed doing this, we want it to give back these variables that we've created. And we do that by saying return, and then just listing out our variables we want to give back. So x grad and y grad. So then you can go ahead and run this cell either by pressing Shift Enter, or you can press this button here. And now we have our function that we can access whenever we want. So let's go ahead and put it to use and say image underscore grad, image grad x and image grad y equals gradient parentheses image gray. So this will take the gradient of our image gray that we've opened here, and it will give back the combined image gradient, or the magnitude, as well as these other gradients that we've defined here. So you can go ahead and press Shift Enter and run the cell. And then we actually want to show what's going on with this image gradient that we've just made. So we're going to do show underscore images, parentheses, then square brackets. And we're just going to type in these three variables here. So you can type them in if you'd like, but you can also just copy and paste as well. Then Shift Enter, and it should start to show you the images. Excellent. Okay, so the first image here is the combined image gradient, or the magnitude. And you can see all of the edges of this bismuth crystal really pop out with this. This one here is the derivative in the horizontal direction. And this is the derivative in the y direction. Okay, so now we have all the tools that we need to actually combine each of these images into one fully focused one. And what we're going to do is make a data container, or a list, of all four of our images here. And to do that, we're going to write the following. So images underscore color, comma, space, images underscore gray equals load underscore images parentheses. And you can go ahead and Shift Enter there. And what we have now are some lists of each of these images in color and in grayscale. And if you're curious, you can just type in images color and see what you get. And you can see, as before, it's these big arrays of data values. The formatting is a little bit strange here because we have 4 different image arrays that we're working with. But anyways, what we're going to do now is that now we have all of our images ready to go. We can do what we want with them. And what we're going to do is we're going to make a loop and iterate through each of these 4 images in this images gray, or through all of the gray images of Bismuth. So the first thing that we're going to do is going to have a data container for our calculated gradients. So we're going to say images underscore grad equals square brackets. And this is just an empty container that is external to the for loop that we're about to program. So for the actual for loop, the way you do this in Python is we're going to say for image underscore gray in images gray, colon. And what this line is saying is that for each image, which I'm calling image gray, in our list of gray images, do something. And the do something that we're going to do is just take the gradient. So we're going to say image underscore grad, comma, space, image underscore grad underscore x, and comma, space, image underscore grad underscore y equals gradient, parentheses, image underscore gray. And again, this is just taking the derivative of one of the images in our image list. So now that we have the image grad, we only are really interested in the overall, the magnitude that we've defined, that image grad there. So what we're going to do is we're going to say images underscore grad dot append. So we're going to add something to our empty list here. And we're going to append that image grad that we've calculated within the loop. And this is going to be able to store all 4 of our image gradients into this external images grad variable or list. So once that's done, you can go ahead and press Shift-Enter to run the code. And everything should be good. So we have our collection of image gradients, and now the task is to select the most sharp aspects of the image, or of each of the 4 images. And the general way that this is done is looking at each of these, each image in this image grad variable, and selecting the pixels with the largest value, or where the slope is the highest, or what parts of the image are most in focus. And to do that, we're going to write the following line of code. We're going to say image underscore gray underscore focused, comma, space, image underscore color underscore focused, comma, space, and image labeled, space, equals. And we're going to be referencing one of the functions defined in the code at the very first cell. That is construct underscore focused underscore image. And as convenience, you notice this kind of highlight here. If you press Tab as you type along, construct focused. Okay, never mind. If you're writing a function, construct focused, sometimes, if you have this come up and you press Tab, Google Colab will finish the function definition for you. Anyways, once you get to that point, you just want close parentheses. And we're going to provide the images underscore grad, the images underscore gray, and the images underscore color. Okay, so this lengthy line, we are calling this construct focused image function. And we're providing the image gradients that we've calculated here, the grayscale images that we've loaded, as well as the colored images as well. And this function will return the one completely focused image that's in grayscale or uncolored, one completely focused image that is colored, and one final image that will show which parts of each corresponding image contributes to the final in-focused image. And you'll see what I mean very shortly. So if you haven't already, just press Shift-Enter to run this line of code. And then we are going to show what we have here. So show images, parentheses, close brackets. And again, we're just going to be using all of these here. So you can go and highlight and control copy and control paste, or you can type it in. And then you go ahead and press Shift-Enter. Okay, awesome. So, as I mentioned, the first image is completely in focused, a single image constructed out of these 4 component images that are partially focused. The second one is in color, and then the final one here shows you, of the 4 different images, which one contributes where. So you can think maybe Bismuth 0 here, if I just bring it up on the side. That it contributes to the back of this fully constructed image. And if I go to Bismuth 3, you can see that it likely contributes to this region here of the fully constructed image. So there you go. That is focus stacking, a little bit of an introduction. I hope that you've enjoyed our tutorial here, and be sure to follow us at McMasterCMS on our Instagram or Facebook. And I hope you have an awesome day.